Hello everyone, and thank you for joining us today. We're really excited to be here in BSides. For me, it's the first time I'm talking in a conference, so I'm a little bit excited. Thank you. And we'll talk today about the Operation CuckooBees that we investigated as part of incident response last year. Before we'll deep dive into the operation, let us introduce ourselves. So my name is Yona. I'm working in Cyber Reason for the past 5 years, and I'm the research director right now. Before that, I was in the incident response team with Ofir and Chen. And 5 years ago, we also spent time together in the Israeli Air Force, and I was the SOC incident response team lead. Chen forced me to add a fun fact about myself, so let's say I love to surf, and show off my adopted dog, Arik. Chen.
Hi everyone, so my name is Chen Erlich. I'm doing incident response at Nocturnal Cyber Reason. Before that, I was senior security researcher at Symptom and senior threat intelligence researcher at Insilo. Besides that, I like to practice Muay Thai and MMA, and I'm doing it for the last 15 years. And you can find me on Twitter.
And lastly, hi everyone. I'm Ofir Ozer. I'm also an incident response engineer at Cyber Reason. Beforehand, I was a Windows malware researcher at Trusteer IBM. I'm also a drummer, and I really like football, the right kind of football, the one with the round ball. And yeah, that's it. Let's begin.
Thanks. So last year, we got an alert for a suspicious credential theft in one of our customers' environments. From there, we kicked in an investigation of months, uncovering the full operation of Winnti that spanned in 3 continents, North America, Asia, and Europe. But before we dive into the operation, let's zoom out for an overview of the whole operation that we dubbed as Operation CuckooBees. So Operation CuckooBees is a espionage campaign. During this campaign, a true APT stole terabytes of sensitive data from the customer's environments and in all of other companies around the world. It was started from an ERP exploit that they found in a public, in an internet-facing server. From there, they deployed web shells in this patient zero. We found that they used novel espionage tools, a rootkit that we dubbed as WinKit, and a really cool abuse of Windows CLFS. As I said, it happened on 3 continents, Asia, North America, and Europe. And it was done by, with highly confidence as Winnti, which is a Chinese nation-state APT, that is also tracked as APT41, Blackfly, and Barium. The motive behind this attack is geopolitics and economical. But before, okay. And now let's get intimate with Winnti, the APT group who did this operation. To understand the motives behind this attack, we need to go back to 2015, when China initiates a national strategic plan that's called Made in China 2025. The plan seeks to engineer China from being a low-end manufacturer to becoming a high-end producer of goods. China's goal was to gain global market domination by achieving independence from foreign suppliers and other countries. To do so, the government chose 10 key sectors that we can see over here that they want to do that. For example, new information technology, energy saving, new materials, and so on. 4 years later, in 2019, the FBI published a research describing China's risk to corporate America. In this report, the FBI summarized the risk that China imposes to the US economy through the hacking program. A few months ago, an FBI director spoke in in this report, they mentioned that the annual cost to the US economy for counterfeit goods, pirated software, and theft of trade secrets is between $225 to $600 billion a year, and China has a big part of it. Also in the report, they state that in order to get this impact, the Chinese government is using illegal ways, such as trading secrets, stealing proprietary data, and from foreign countries. And to achieve this goal, Winnti acts. And we believe that this operation is part of it. Over the years, the Winnti group initiated thousands of successful attacks, getting headlines all over the world. And a few months ago, an FBI director said in the 60 Minutes show that the biggest threat for the American law enforcement is from Chinese hackers stealing proprietary information. According to him, the Bureau opens a new China counterintelligence investigation about every 12 hours. And we can see his quote from this show: "They are targeting our innovation, our trade secrets, our intellectual property at a scale that is unprecedented in history. They have a bigger hacking program than all other major nations." So now that we understand the motives behind this attack, let's go back to Winnti and get intimate with them. So as I said, Winnti is a Chinese APT, a nation-state APT. They are active from at least 2010 until today, and they have three focus areas. They are state-aligned cyber espionage, IP theft, and cybercrime, including ransomware, cryptocurrency miners, and fraud. And they are active worldwide. So what is Operation CuckooBees? Operation CuckooBees is a multi-year cyber espionage intrusion. During the investigation, we found that the intrusions are there from at least 2019, and they were undetected, with the goal of stealing IP from tech and manufacturing companies around the world. During the investigation, we could attribute the operation to Winnti, the Chinese threat actor, and we could uncover the latest techniques and their playbook that we will describe in the presentation. We found some evasive and rare techniques and newly discovered malware and rootkit that we will talk about it later. So let's go deep and understand how they did everything and what is the kill chain in the attack. So it's all started from externally facing server exploitation. After they got in, they moved to install persistence. Then they did two phases of reconnaissance that we split into initial and advanced. The next phase was credential dumping. After they got their credentials, they moved laterally between the servers and machine in the environment. And the last phase was data collection and exfiltration. So the entry point in this operation was scanning. Winnti scanned the internet looking for externally facing servers that has vulnerabilities. In this case, they found the famous ERP server, and they found multiple RCA vulnerabilities that they exploited. After they exploited it, they looked for this specific DLL that was on the VMware Tools folder. That it was loaded by the dropper and was supposed to inject to SVC host this DLL. This is also might be an indication of an older attack that had already been there and wanted to check if the DLL is already there. From there, they moved to persistence. We can see here the web shells. We found dozens of web shells installed in patient 0. And they put JSP code in the web shells. By looking these web shells online, we could find in Chinese forum, hackers forum, and in GitHub the existence of the web shell from 2006, and this is also one of the TTPs of Winnti. After we started to block them, they tried to gain additional persistence mechanism, and they moved to use WinRM. WinRM is a Windows capability that by enabling that, they got remote shell access over HTTP and HTTPS. We can see here the command line that they used to enable WinRM. And the last way of persistence was DLL sideloading. They performed DLL sideloading to persist through a legitimate Windows service. In this case, it's a print notify service. They sideload into it at dbghelp. That Chen will talk about it later. We called it deploy log. From there, they moved to reconnaissance. As I said, we split the reconnaissance into two phases, initial reconnaissance and advanced reconnaissance. Here, the first commands that they used were cadTCOS and root print, which gave us the lead that they use automated scanning tools. Since this is a Windows server and cadTCOS is a Unix command, after they understand they are running on Windows, they started to run commands such as systeminfo, netstart, netuser to gain more information about patient 0. The next phase of reconnaissance was using a schedule task that deploy batch file in this schedule task that their content changed from phase to phase and from machine to machine. The content contained lol bins, leaving off the land binaries, which are Windows built-in executables to evade detection. And we can see here some of the used command, fsutil, ipconfig, netstat, and so on. Now that they understand what is the network that they are working on, they wanted to gain credentials so they can move laterally. And we found this first technique. They used undocumented executable at the time of the investigation that called MFS-DLL. And in one of these commands, in the same command, we observed loading of Mimikatz module, which is a well-known tool for credential theft. The second way of credential theft was dumping the registry. So they dumped the system and SAM security hives. And using that, they got more credentials on patient 0. The next phase was the lateral movement using schedule tasks. So this is the same schedule task with the batch file that we saw in the reconnaissance phase, and now the content changed for lateral movement. Their goal was to find a machine that has domain admin credentials, and after they got it, they started to move laterally between different regions, different continents, and different domains within the customer environments. We can see here the command that they use. So they use schedule task with the IP address and username and password that they install of the domain admin. They run it only once on each machine. They call it test to blend and to sim a legitimate schedule tasks. Then they gave the path to the batch file and run it as a system user. The last phase of the attack was data collection and exfiltration. We find that they used a renamed WinRAR, an archive tool. In this case, it was a Chinese WinRAR that we can see here from VirusTotal. They renamed it to run DLL32 to evade detection. And here, this was our aha moment when we understand that they are staging the most sensitive data of the customer, formulas, blueprints, manufacturing data, and so on. Now I will hand it to Ofir that will talk about the malware arsenal that we found in the operation.
Thank you, Niv. Hi, everyone. Glad to get this reception. So, I'm going to talk to you about the many different samples that Winnti used in order to infect a single machine. Okay? We will use this map, this diagram, in order to get over the full flow of Winnti's infection. Using this technique, they were managed to infect many different machines in the different organizations that they were into. When we will go over the different stages, we will also talk about the very cool techniques that they've used in order to be more evasive and be more stealthy. Let's go over like this diagram really quickly. So you have all the first steps that Niv talked about during the kill chain explanation. And as Niv said, it all started with a batch execution. It has the ability to run some reconnaissance, but we've seen that the first thing that's running in the infection chain is the spider loader, which brought the first files to the machine. Then, stash log was used in order to stash a lot of encrypted payloads to the CLFS log, and we will discuss the CLFS log in a bit. Then Spark log was the first sample that really extracted information from the CLFS log and deployed the persistent part private log to the infected machine. Private log then deployed the user mode agent, which is deploy log, and then deploy log also deployed the kernel mode agent, which is WinKit. Now I know it's a lot. Let's take it step by step, and we will start at the beginning with the spider loader. So Spider Loader, as I said before, is the first binary that got executed on every machine. It got executed by a batch scripts that were dropped that was executed using the schedule task, and we've seen it delivered in two different flavors. The first one was an exe file. The second one was a DLL file. In both cases, what they wanted to do is masquerade as an SQLite 3 component. In the case of the exe file, it was very simple, very straightforward, just SQLite3.exe, nothing really special. But in the case of the DLL, they did something very interesting. They just kept the DLL as it is, but changed the function in the ordinal number of 138 to carry on their malicious operations. What it did is loaded a file that was given in an argument, as you can see here, if you can see it, a TLB file, which of course is not a normal TLB file, but an encrypted file, decrypted it and dropped the next files that it needed to the attack. We also seen that it had some rat capabilities. We based it on older spider investigations, and across different machines, we found it in different locations and with different names, because you want to be diverse. So while we were investigating this part, we found a very cool anti-hooking technique. So first of all, let's talk about a hook. What is it? A hook basically is an augmentation of behavior of any software component by intercepting a function, an event, or something like that, and augmenting its behavior in some way. Well, it's a nice explanation, but let's see it graphically, and I did it with animations, so it's way better. So let's say that you want to hook the LDR load DLL function, for example, all right? So we have the first assembly lines, setting the stack for further execution, everything is fine. If we want to hook it, and I'll give an inline hooking example, what I can do is just patch the targeted function to jump to a proxy function. And this proxy function will carry on the different activities that I want it to do. In most cases, almost every cases if we're talking about security systems, the proxy function will jump back to the targeted functions and also carry on the first instructions that were supposed to carry on in the overwritten the function itself. We know that a lot of EDR solutions, a lot of security solutions use this kind of mechanism in order to monitor API calls. So you can see where I'm going with it. Winnti wanted to get over those mechanisms, so they targeted those functions that are usually targeted by EDR solutions, and they wanted to unhook them. So how did they manage to do it? This is our NTDLL that is loaded to memory. What they have done is they copied ntdll.dll from disk to a different file name that called tn, a bunch of random characters, .dll, and load it to memory. Then it just compared the first bytes of the already loaded NTDLL to the one that was copied from disk. In case of a mismatch, what they did is just overwrite the NTDLL one that was already loaded, and by this way just went over the installed hook in case that it was there. So now that we talk about the spider loader, we brought the tools, everything is in there. Let's go on to the next stage, which we dubbed as the multi-phased arsenal deployment. Ooh. So this deployment stage heavily relies on the Windows CLFS mechanism in order to store and extract different samples and different payloads in order to stay stealthy and what's not. And we'll discuss the other goals later. So first of all, what is the CLFS? So the Windows CLFS is a Windows logging mechanism that provides high-performance logging for various different goals. It heavily used in the Windows kernel transaction manager, both for transactional registry operations and transactional file systems. Both transactional subsystems allow the ability to log different changes, commit them, and even roll back in case of an error or any reason that will be. In order to use it, Windows employs a proprietary file format that calls BLF that is not really documented, and we haven't found any any usable parsers online in order to decrypt these BLF files. And it can only be accessed by the CLFS API function calls. On this, the CLFS log consists of two file types. The first one is the BLF itself, which is the log metadata, and one or more container files, which contains the different log data. If we look at this example, you have like the BLF file of the end-user.hive, which contains, as I said, the metadata, and we have two container files, which contains the information itself. So now that we know what the CLFS is on a high level, let's talk about the first component that really uses it, which is stash log. Stash log basically just stashing different payloads to a CLFS log, and in this way just prepares the victim for the next phases of the infection. Stash log has two different modes of execution. The first one, without any different arguments, it just creates an atom from a random generated GUID and store it into the global atom table. The global atom table is a table in Windows that allows the ability to share different strings using different int identifier between different processes. And even the same processes, but on different times. This was like without any argument. With one argument, it's used to really store all the encrypted payloads. But in order to do it, it depends on the stored atom from before. So how is it able to do it? First of all, the argument given to stash log is an encrypted buffer that, first of all, gets decrypted using the GUID from the atom. Then, after decrypting it, it checks like the file validity, because you need to know that you're doing something in a good way or not. Then it looks for the destination BLF file in order to store everything, which is the default user end-user.hive BLF file. If it's not created for some reason, it creates it, but in both ways, it clears it. Then it encrypts the malicious data it decrypted from before, but this time using different machine characteristics and storing everything to the BLF container file itself. Now, when we first started investigating stash log, this was what greeted us on IDA Pro. And as you can imagine, like this was our reaction. Yeah, what can you do? So how did they manage to do it? Well, it was a very cool trick that basically what they've done is tricking disassemblers into parsing if statements as switch case statements with a lot of different potential cases. If we look at this example, this is a very normal if statement on assembly. You have like your check, and then you have a jump with two different objects. Straightforward, everything is working, right? Well, cool. Winnti wanted to be like smarter than this, and what they did is return the check result to a different jump list, which contain different nodes in the function. This way, any disassembler that we try to work with just parsed it as a switch case check with a lot of different options. In this example in particular, we had 332 different objects. Yikes! Whew. So, we talked about stash log. We talked about how everything was stored in there. Let's talk about the first extractor from the CLFS log, which is Spark log. Spark log, very, very simple and straightforward. What it does is extracting a payload from the CLFS log and set it up to be launched by a legitimate Windows service. This DLL is private log, and we will talk about private log in a bit. And it's set it up to be loaded by either the IKEX service in Windows Vista to Windows 7. The IKE service is the service that's in charge of the internet key exchange and the authentication IP protocol in Windows. And in Windows 8, going forward, it was sideloaded to the print notify service, which is in charge of all the interactive printing operations in Windows. So, now that we talked about it all, I will give my mic to Chen.
Thank you, Ofir. Okay, so let's do a quick recap. So what we see on the left is the kill chain. The batch file that is being executed can be used for reconnaissance, but on infected machines, it's being used not mostly, but all the time for this infection change. So it starts with a spider loader, some kind of a rat. Then stash log is being executed to stash all the encrypted payloads within the CLFS log file. Then spark log kicks in. Spark log extracts private log, and then we get into private log. So what is this private log? So private log is the persistence and privilege escalation component in the infection chain. It deploys and then executes deploy log, the next link. So the first phase is dropping deploy log. So it extracts and decrypts deploy log from the CLFS log file and copies a legitimate dbglp.dll from system32 to its newest location under the Windows PowerShell directory. Then it uses a pretty unique DLL loading technique to load and execute deploy log. So before we go over the technique, let's remind ourselves a bit about NTFS transactions. So NTFS transactions are based on CLFS, and they enable basically to record a set of actions on the NTFS file system, such as edit, remove, or create files or directories, and then commit them at once or roll them back at once. The attackers used in deploy log the transactional API calls, to move on to deploy log and gain stealthiness. So it first starts using the create transaction and create file transacted API calls, which create a transaction handle to the new DBGL. Then they override the transacted dbgl.dll with a decrypted payload. Then they create a memory section and load the transacted file to this section in memory. The next step is fixing the section permissions and resolving the DLL imports, and then executing deploy log's entry point. This loading scheme is pretty similar to the Phantom DLL hollowing, but it's a bit different. So after deploy log has been executed, let's move on and discuss deploy log. So deploy log was discovered as dbgl.dll, and it has two purposes. The first one is the rootkit deployment. It deploys the rootkit and communicates with it. The second hat is the user mode agent. So it acts as a user mode agent. It communicates with the remote C2 and holds some rat capabilities. Before we dive into rootkit communication, let's discuss a bit background on rootkit communication. So basically, there are a few ways to communicate from user mode to kernel level. Among the ways is using device object and IOCTLs. In Windows, you can use the device IO control API call as an interface for IOCTL, which is an input and output control, to basically send control codes to the kernel level. The kernel level gets these control codes, acts upon these control codes, and returns data if needed. So deploy log initiated a communication channel by acquiring a handle to the BIP device. If it failed, it acquired a handle to the null device. Both of these devices are used a lot of times in operations that involve rootkits, mainly the null device. Then it sends an IOCTL request to test if the rootkit was already deployed. If it wasn't deployed, then it starts deploying it. So it extracts the decrypted WinKit, which is the rootkit, from the CLFS log file. It stops the AMD K8 service, which is the AMD processor kernel driver service. This is pretty interesting because aiming for this service might tell something about the attackers and about the victims. It might tell that basically they had some prior intelligence on the victims, on the processors, and based on this intelligence, they decided what to aim for. So they aimed for this AMDK8 service. They changed the AMDK8 service execution path to the following path and wrote a WinKit driver to this path exactly. Then they started the service which executed the driver and restored the service to its default state to enable a successful reboot. The second hat of deploy log is the user mode agent. So as a user mode agent, it communicates with the C2. The received data from the C2 is intercepted by the driver, and we'll discuss it later. And it holds some RAT capabilities, so it can execute some CMD commands and download and execute payloads such as the mfs.dll credential grabber that Niv talked about before. And this gets us to our last step, the cream of the crop, the king, WinKit. So WinKit is Winnti's rootkit in this operation. It was discovered as bqdsp.sys. It's the kernel level component of the agent, receives commands from deploy log and from the C2, and hooks TCP/IP communication by directly talking with the network card. So an interesting thing about WinKit is that the compilation timestamp is from 2019, but until we published the blog post, which was in 2022, it had almost a 0% detection rate on virus total. Only one vendor alerted the WinKit as malicious, while others said it's a good file. So it has also interesting signatures. So it contains an expired BenQ digital signature, which was stolen. It was expired on 2015. BenQ generally is a Taiwanese manufacturer of electronic devices, mainly displays. It leveraged this digital signature, which you can see a bit information about how they try to disguise, to bypass the driver signature enforcement mechanism, which Windows contains, which is basically enforces, called DSC, basically enforces only verified digitally signatured drivers to load in Windows and kicked in starting from Windows Vista. So we talked about study characteristics. Let's talk about execution a bit. So it hooks, after successfully loading, it hooks the network communication. To do so, it uses the Windows ND API to communicate directly with the network card. It enables the threat actor to hide their network communications. So during investigation, if WinKit executes, if you write netstat, for example, you wouldn't see the communication. It will be hidden. And it can receive the following commands from deploy log. So the commands are, the first command that can be triggered is to hide the driver in memory. When this command is triggered, then WinKit deletes its headers from memory and removes the driver from the driver's linked list. The second ability is to communicate with the C2 directly without going through the process of user mode kernel. It has also the ability to return the rootkit's version to deploy log or any other user mode agent that WinKit will deploy, and also to clean up. So let's wrap up everything. It starts with a batch execution. Spider loader goes next. Stash log right afterwards. Stashes all encrypted payload to the CLFS log in a very stealthy way. Spark log executes. It extracts private log to gain persistency and privilege escalation. Private log extracts deploy log in a very cool way. Deploy log has two hats. The first hat is deploying WinKit, and the second hat is acting as the user mode agent, and WinKit being WinKit working as a rootkit in the kernel level. So some detection ideas, because we are here for the blue teams. So first of all, you can use the IOCs and the command lines from this presentation, from the blog post. You can use some Yara rules. Some of them are publicly available to hunt for this operation, or you can create them by yourself. You can hunt for CMDs executed from the jlaunch.exe, which is the executable that was used in the ERP solution, and also from SVChost. You can look for API calls from unusual processes to the BLF file and its container files. And lastly, we can use our old friend volatility. Using the unloaded modules command, you can see if the driver was unloaded in the past using this name, disguising as a BenQ related driver. So the key takeaways to wrap up the operation. So first of all, we managed to discover worldwide, truly global and impactful APT IP theft in alignment with China's notorious Made in China 2025 plan. This operation emphasizes the importance of network hygiene, so the affected victims haven't had any good network hygiene, so that's what managed them to laterally move, to dump credentials, to move between continents. So they had unpatched systems, insufficient network segmentation, no multi-factor authentication, and so on. We managed to get also a rare glimpse into Winnti's hacking playbook to understand how they infiltrate, how they act, how they move, what they think, and how they react. And we managed to get a deep dive into Winnti's arsenal. So we discovered new malware and new versions of known malwares. And we got a sneak peek into their enhanced stealth House of Cloud approach, which is pretty interesting, hiding in CLFS. So we would like to also acknowledge our teammates that did an awesome work with us on this research. And that's it. You can follow us on Twitter and further read in our blog post. Thank you.